A submersible pump can indeed function as a sacrificial anode in both saltwater and freshwater environments. This is because a sacrificial anode, by definition, is a metal strategically employed to corrode more readily than the metal it is intended to protect. When these two dissimilar metals are electrically connected with an electrolyte, such as saltwater or freshwater, the sacrificial anode preferentially undergoes oxidation, thereby shielding the protected metal from corrosion. Submersible pumps are frequently constructed from materials like stainless steel or cast iron. These metals exhibit a relatively high susceptibility to oxidation, rendering them suitable for serving as sacrificial anodes for other metals present in the system, such as aluminum or copper. Now let's consider the implications of applying an electrical current to a submersible pump that is already acting as a sacrificial anode. In this scenario, the rate of corrosion experienced by the pump will be accelerated. The introduction of electrical current effectively amplifies the oxidation reaction, hastening the degradation of the sacrificial anode material. While this accelerated corrosion may lead to a reduction in the pump's overall lifespan, there are instances where it can prove advantageous. For example, in highly corrosive environments, the increased corrosion rate of the submersible pump, acting as a sacrificial anode, can provide enhanced protection to other metallic components within the system. It is crucial to consider the principles of galvanic corrosion to fully grasp this phenomenon. Galvanic corrosion arises when two dissimilar metals are immersed in an electrolyte and are electrically connected. This creates a galvanic cell, where one metal acts as the anode, corroding preferentially, while the other acts as the cathode, being protected. The driving force behind this corrosion is the difference in electrochemical potential between the two metals. Metals with lower electrochemical potentials, such as zinc or magnesium, are commonly used as sacrificial anodes to protect metals with higher electrochemical potentials, such as steel or copper. The choice of sacrificial anode material is determined by factors such as the environment, the metal being protected, and the desired lifespan of the protection system. In the context of submersible pumps, the material of the pump itself can act as a sacrificial anode, protecting other metallic components in the system. However, it's important to note that the effectiveness of this protection depends on factors such as the conductivity of the water, the surface area ratio between the pump and the protected metal, and the presence of other corrosive agents in the environment. To mitigate the potential for accelerated corrosion when electrical current is applied, several strategies can be employed. Firstly, ensuring proper grounding of the submersible pump and associated electrical systems is paramount. This helps to minimize stray electrical currents that could exacerbate corrosion. Secondly, the use of corrosion-resistant coatings in the pump surface can provide an additional barrier against corrosion. These coatings can be applied through various methods such as painting, powder coating, or electroplating. Thirdly, implementing cathodic protection systems can further enhance corrosion protection. Cathodic protection involves applying an external electrical current to counteract the natural corrosion process. This can be achieved through the use of sacrificial anodes or impressed current systems. Sacrificial anodes, as discussed earlier, are metals that are more easily corroded than the metal being protected. They are strategically placed in the environment to corrode in place of the protected metal. Impressed current systems, on the other hand, use an external power source to drive a current through the electrolyte, thereby polarizing the protected metal and reducing its corrosion rate. When selecting a cathodic protection system, it's important to consider factors such as the size and shape of the structure being protected, the conductivity of the electrolyte, and the desired level of protection. Regular monitoring and maintenance of the cathodic protection system are also essential to ensure its effectiveness. In addition to these mitigation strategies, proper material selection plays a crucial role in minimizing corrosion. Choosing materials that are inherently resistant to corrosion in the specific environment can significantly extend the lifespan of the submersible pump and other metallic components. For example, using stainless steel alloys with high chromium and molybdenum content can improve their resistance to pitting and crevice corrosion in chloride-containing environments. Furthermore, avoiding the use of dissimilar metals in close proximity can help to prevent galvanic corrosion. If dissimilar metals must be used, they should be electrically isolated from each other to minimize the flow of current between them. In some cases, the deliberate application of electrical current to a submersible pump acting as a sacrificial anode can be used for specific purposes, such as accelerating the removal of rust or scale from the pump's surface. This process, known as electrocleaning, involves using the pump as an electrode in an electrolytic cell with the application of a controlled current to dissolve the unwanted deposits. However, electrocleaning should be performed with caution, as excessive current or prolonged exposure can damage the pump's material. It is important to carefully monitor the process and use appropriate electrolytes and cleaning parameters. In summary, submersible pumps can indeed act as sacrificial anodes in both saltwater and freshwater environments. The application of electrical current to the pump can accelerate the corrosion rate, which may have both beneficial and detrimental effects. Implementing proper grounding, corrosion-resistant coatings, cathodic protection systems, and careful material selection are essential for mitigating corrosion and extending the lifespan of submersible pumps in corrosive environments. Let's delve into some specific examples to illustrate these concepts further. Imagine a submersible pump installed in a saltwater well. The pump's casing is made of stainless steel 304, while the well casing is made of carbon steel. In this scenario, the stainless steel pump casing can act as a sacrificial anode, protecting the carbon steel well casing from corrosion. The difference in electrochemical potential between the two metals drives a galvanic current, causing the stainless steel to corrode preferentially. Over time, the stainless steel casing may experience localized pitting or crevice corrosion, but the carbon steel well casing will remain relatively protected. Now, suppose that an electrical fault occurs in the pump's motor, resulting in a stray current flowing through the water and the pump casing. This stray current will accelerate the corrosion of the stainless steel casing, potentially leading to premature failure. To mitigate this risk, it is crucial to ensure that the pump's motor is properly grounded and that any electrical faults are promptly addressed. Another example involves a submersible pump used in a freshwater lake. The pump is made of cast iron, while the impellers are made of bronze. In this case, the cast iron pump body can act as a sacrificial anode, protecting the bronze impellers from corrosion. The cast iron will corrode preferentially, forming a protective layer of iron oxide on the surface. This layer can help to slow down the corrosion rate of the cast iron and extend the lifespan of the pump. However, if the water in the lake is highly acidic or contains high levels of dissolved salts, the corrosion rate of the cast iron may be significantly increased. In such cases, it may be necessary to use a more corrosion-resistant material for the pump, such as stainless steel or a polymer composite. Furthermore, the application of electrical current to the pump, such as through an impressed current cathodic protection system, can further reduce the corrosion rate and extend the lifespan of the pump. It is important to note that the effectiveness of a submersible pump as a sacrificial anode depends on a variety of factors, including the water chemistry, the materials of construction, and the presence of electrical currents. Regular inspection and maintenance of the pump are essential to monitor its condition and to take appropriate measures to prevent corrosion. This may involve cleaning the pump's surface, applying corrosion-resistant coatings, or replacing sacrificial anodes. In addition to these practical considerations, there are also some theoretical aspects to consider. The corrosion rate of a metal is determined by the kinetics of the electrochemical reactions that occur at the metal electrolyte interface. These reactions involve the transfer of electrons between the metal and the electrolyte, and their rates are influenced by factors such as the electrode potential, the temperature, and the concentration of reactants. The Nernst equation describes the relationship between the electrode potential and the concentration of reactants. It can be used to predict the corrosion potential of a metal in a given environment. The Porbix diagram is a graphical representation of the thermodynamic stability of different metal species as a function of electrode potential and pH. It can be used to identify the conditions under which a metal will corrode or passivate. Understanding these theoretical concepts can help engineers to select appropriate materials and corrosion protection strategies for submersible pumps in various environments. In conclusion, the role of a submersible pump as a sacrificial anode is a complex phenomenon that depends on a variety of factors. By understanding the principles of corrosion and the factors that influence it, engineers can design and operate submersible pumps in a way that minimizes corrosion and extends their lifespan. Remember to consult with qualified professionals for specific applications and to follow all applicable safety guidelines. Now let's talk about the different types of corrosion that can affect submersible pumps. Firstly, there's uniform corrosion, which is a relatively even attack over the entire surface of the metal. While it's predictable, it can still lead to eventual failure. Secondly, galvanic corrosion occurs when two dissimilar metals are in contact in an electrolyte, as we've discussed extensively. Thirdly, pitting corrosion is a localized attack that creates small holes in the metal. These pits can be difficult to detect and can lead to rapid failure. Fourthly, crevice corrosion occurs in shielded areas, such as under gaskets or washers, where there's a stagnant electrolyte. Fifthly, erosion corrosion is caused by the combined effect of corrosion and erosion due to the movement of fluids. Sixthly, stress corrosion cracking is a type of failure that occurs when a metal is subjected to both tensile stress and a corrosive environment. Finally, dealloying is the selective removal of one or more elements from an alloy, leaving behind a weaker material. When it comes to selecting materials for submersible pumps, it's important to consider the specific environment in which the pump will be used. For example, stainless steels are generally resistant to corrosion in many environments, but they can be susceptible to pitting and crevice corrosion in chloride-containing environments. Copper alloys are often used for impellers and other components that require high strength and good corrosion resistance. However, copper can be susceptible to galvanic corrosion when in contact with steel. Plastics and composites are increasingly being used in submersible pumps due to their excellent corrosion resistance and lightweight. However, they may not be suitable for high temperature or high pressure applications. Regular inspection and maintenance are critical for preventing corrosion in submersible pumps. This includes visually inspecting the pump for signs of corrosion, such as rust, pitting, or cracking. It also includes testing the water chemistry to ensure that it is within acceptable limits. If corrosion is detected, it's important to take corrective action immediately, such as cleaning the pump, applying corrosion-resistant coatings, or replacing damaged components. In some cases, it may be necessary to modify the operating conditions of the pump to reduce the risk of corrosion. For example, reducing the flow rate or temperature of the fluid can help to slow down the corrosion rate. Finally, it's important to keep accurate records of all inspections and maintenance activities. This will help to track the performance of the pump over time and to identify any potential problems early on. By following these best practices, you can significantly reduce the risk of corrosion and extend the lifespan of your submersible pumps. In addition to the points already discussed, it is worth considering the role of microorganisms in corrosion. Microorganisms such as bacteria and fungi can accelerate corrosion through a process called microbiologically influenced corrosion, or MIC. MIC can occur in a variety of environments, including water, soil, and even air. It is often difficult to detect and can cause significant damage to metallic structures. Microorganisms can promote corrosion through several mechanisms. Firstly, they can produce corrosive substances such as acids, sulfides, and ammonia. Secondly, they can create biofilms on the metal surface, which can trap corrosive substances and create localized corrosion cells. Thirdly, they can alter the electrochemical potential of the metal, making it more susceptible to corrosion. To prevent MIC, it is important to control the growth of microorganisms in the environment. This can be achieved through the use of biocides, which are chemicals that kill or inhibit the growth of microorganisms. Biocides can be added to the water or applied to the metal surface. It is also important to maintain good hygiene practices such as cleaning and disinfecting equipment regularly. Furthermore, it is important to select materials that are resistant to MIC. Some metals, such as stainless steel and titanium, are more resistant to MIC than others. In addition to material selection and biocide treatment, cathodic protection can also be effective in preventing MIC. Cathodic protection can reduce the corrosion rate of the metal, making it less susceptible to attack by microorganisms. Furthermore, it is important to monitor the environment for signs of MIC. This can be done by testing the water for the presence of microorganisms and by inspecting the metal surface for signs of corrosion. If mica is detected, it is important to take corrective action immediately to prevent further damage. This may involve cleaning the metal surface, applying biocides, or modifying the operating conditions of the equipment. Let's consider the specific case of submersible pumps and wastewater treatment plants. Wastewater contains a variety of microorganisms as well as corrosive substances such as sulfides and ammonia. This makes submersible pumps and wastewater treatment plants particularly susceptible to mica. To prevent mica in these pumps, it is important to use corrosion-resistant materials such as stainless steel or titanium. It is also important to treat the wastewater with biocides to control the growth of microorganisms. Furthermore, it is important to inspect the pumps regularly for signs of corrosion and to take corrective action as needed. Finally, it is important to maintain good hygiene practices in the wastewater treatment plant to prevent the spread of microorganisms. Another important factor to consider is the effect of water velocity on corrosion. High water velocities can accelerate corrosion through a process called erosion corrosion. Erosion corrosion occurs when the protective layer on the metal surface is removed by the abrasive action of the water. This exposes the bare metal to the corrosive environment, leading to increased corrosion rates. To prevent erosion corrosion, it is important to maintain appropriate water velocities. The optimal water velocity will depend on the specific materials and the environment. In general, low water velocities are preferred to minimize erosion corrosion. It is also important to ensure that the water is free of abrasive particles such as sand and silt. These particles can accelerate erosion corrosion. Furthermore, it is important to avoid sharp bends and constrictions in the piping system. These features can create localized high-velocity areas, which can lead to erosion corrosion. In addition to water velocity, the temperature of the water can also affect corrosion rates. Higher temperatures generally accelerate corrosion rates. This is because higher temperatures increase the rate of electrochemical reactions. To minimize corrosion at high temperatures, it is important to use corrosion-resistant materials and to control the water temperature. It is also important to avoid localized hot spots, which can accelerate corrosion. In some cases, it may be necessary to use cooling systems to maintain the water temperature within acceptable limits. Finally, it is important to consider the effect of pressure on corrosion. High pressures can accelerate corrosion through a process called pressure-enhanced corrosion. Pressure-enhanced corrosion occurs when the pressure increases the solubility of corrosive substances in the water. This can lead to increased corrosion rates. To minimize corrosion at high pressures, it is important to use corrosion-resistant materials and to control the water pressure. It is also important to avoid pressure fluctuations, which can accelerate corrosion. In some cases, it may be necessary to use pressure-reducing valves to maintain the water pressure within acceptable limits.